So this question is from module 5, mass transfer region. So we have a oxygen gas at 25 degrees Celsius and pressure of 2 bar is flowing through a rubber pipe. Okay, so there is a rubber pipe, and inside that rubber pipe a oxygen gas which is maintained at a temperature of 25 degrees Celsius and pressure of 2 bar. Okay, it's flowing. And inside diameter of the pipe is given as 25 mm. The wall thickness, obviously it must be cylinder, so it would have some thickness. The thickness is 2.5 mm. And other data given in the question are the diffusivity of the oxygen through rubber. So the oxygen gas is flowing inside the rubber tube, right? So obviously it would diffuse into the rubber. So D, the diffusion coefficient or diffusivity of oxygen is given as 0.21 into 10 raised to minus 2 meters square per second. And solubility of the oxygen in the rubber is also given. We have to determine the rate of loss of oxygen by diffusion per meter length of pipe. That means we have to rate of loss of oxygen means we have to find the mass flow rate. Okay, so let's look how to solve this problem. So in this question, first of all, writing all the given condition we have. Diffusivity D is given. Length they have mentioned the thickness. Since it is diffusing along the thickness, we have to take it as length. Okay, and it has to be converted into meter because we have the diffusivity in meter, so we have to convert the mm into meter. Similarly, the inside diameter, which is also given in millimeter, has to be converted into meter by multiplying it with the 10 raised to minus 3. Okay, solubility of the oxygen gas with the rubber is given. The first thing we have to find is a molar concentration. As the first thing we have to find it, molar concentration inside. I'm calling the inside region as A1. So molar concentration inside the tube and molar concentration outside the tube. So to find if you know the solubility and pressure at a particular stage, a particular situation, then we can find the molar concentration, right? So we know the solubility of oxygen gas. It is given in the question. And the pressure inside the rubber tube at which the oxygen maintained is also given 2 bar. So we can find the molar concentration inside the tube by solubility in pressure. Okay, but we don't have one data to find the molar concentration outside the tube because we don't have the pressure at which the oxygen maintained outside the tube. So outside the tube means the atmosphere. Not to find that they are given and data in this question. That means the molar proportion of oxygen in air is mentioned as 21 percentage. That means the percentage, the more number of moles or proportion at which the oxygen can be seen in the atmosphere of air is given as 21 percentage. With that data, I can find the pressure of oxygen outside the tube because the atmospheric pressure that is 1 bar we know. So not to find the pressure of oxygen outside the tube in the atmosphere, we have to multiply the molar proportion of oxygen with the atmospheric pressure 1 bar. So we get 0.1 bar. So now I can find the molar concentration outside the tube Ca2 by solubility in this pressure. Now we got uh, molar concentration both inside and outside of the rubber tube. So this will be the equation we'll be using to solve this problem. So many way you can solve this problem. So since I have find out the molar concentration Ca1 and Ca2, I need to use this molar flux equation. There is mass flux equation as well as molar flux equation. So if I am taking mass flux equation, I need to find the mass concentration. Okay, rho A1 and rho A2. I need to know that, but since we don't have that value and I find out the molar concentration, I need to take the equation of molar flux. So molar flux means like it is given by this equation Na by A into dAb into Ca1 minus Ca2 by L. For L is the thickness, dAb is the diffusivity, Ca1 and Ca2 are the molar concentration are inside and outside. A is the area, surface area, and Na is actually basically it's a number of moles. Okay, number of moles per second. That's what's Na by A. So next step is I need to find the area. Okay, I need to find the area. Area can be, since we have the length and diameter, you can simply find it by pi dl. Okay, just use pi dl. We can find the area. So area will be this much value. And now we need to, here we need to find Na. That means this number of moles we need to find. Okay, so Na can be found out by this this area can be given this transfer into this side. So now we got the Na number of moles as this much value 3.68 into 10 raised to minus 8 kilogram mole per second. Actually, if it is number of mole, you may think it is kilogram mole, right? But how does it second come? Because it is actually some mole rate is actually in this equation is actually mole rate, not simply number of moles. Is mole rate. Okay, so the unit will be kilogram mole per second, not simply kilogram mole. So now we got the number of moles. So we know the relation between like mass and number of moles. Here I can say it as mass flow rate by number of mole flow rate equal to the molecular weight. So even if you remove this rate equation, we know the equation to find number of moles, which is mass in gram by molecular mass. The same way we can find here. So since we have to find the flow rate, rate they have asked the question to find the oxygen rate. So we need to find the m dot a. That means mass rate we need to find. So we have mole rate. So what we have to do is just multiply the molecular weight with the mole rate. We know mole rate, we just find out, and molecular weight of oxygen will be 32. So our answer is the the mass rate is equal to 1.17 into 10 raised to minus 10 kilogram per second.